students, welcome to the next lecture of electronic measurements and instrumentation. My name is 𝑘𝒊𝒅𝒕𝒉. In this class, we will see the concept of square and pulse wave generators. In the previous classes, we have seen different types of signal generators. We have started the signal generators concept with the basic standard signal generator, and then we have seen the conventional standard signal generator. Then we have seen AF sine and square wave generators. After that, we have seen the concept of function generators. Okay, now we are going to see the concept of sine and square wave we will see the concept of square and pulse wave generators. So first we will see the square and pulse wave information. Sometimes the signal generators we are calling as oscillators also. Coming to that, the signal generators are used for measuring in the combination with a CRO. So some of the function generators which are delivering the signals, these are all the signals we can check with the help of a CRO. They provide both quantitative and qualitative information and the system under test. So signal generators, they will provide the quality of the signals and the quantity of the information we can measure with the help of CRO. They are made use of transient response of testing amplifiers. So we will test all these circuits behaviors with the real time of amplifiers. For example, take CE amplifier. When we are going to check this CE amplifier characteristics or the outputs, we need a signal generator as an input for the CE amplifier. So after giving this input signal to the CE amplifier output we are observing at the CRO. The CRO will gives the input signal how it is amplifying under the common emitter configuration for different types of transistors in the amplifier process. So coming to that, so whatever it may be, the output of these signals sometimes we are seeing in the form of a square or pulse waveform. How to differentiate these two signals? The square and pulse wave signals, we have to differentiate. So before going to differentiate, first of all, the square and pulse waveforms has a common term that is called duty cycle. The duty cycle of a sinusoidal of a square waveform or a pulse waveform, we are analyzing with this ratio of pulse width to pulse period. Generally, the duty cycle is nearly 50% the square wave generators for the square wave signals. For the square wave signals, the duty cycle is 50%. Okay, right. So, whichever the logics we are maintaining, high level logic and low level logic, this high level and low level logics, one combination of one square wave. So see here, this is a square wave. This is one square wave. In this square wave, the time period of high level logic or the time period of low level logic, if these two time periods are equal, then we are calling this signal has the duty cycle of 50%. That is the total time period of one positive and negative logic time period and the duty cycle. The duty cycle we will calculate with the help of, this is the pulse width. So this is the parameter called pulse width. This is a parameter called pulse period, PP and PW. The pulse width and pulse period. If you take the ratio of the pulse width and pulse period into 100, then the value, if you are getting 50%, then you are calling as the square wave. That is the positive logic and negative logic has both the same time periods. For generally square wave has this type of property, but for the pulse it may be same or it may be different. It has different types of characteristics. So for that, first we have to see the requirement of a pulse generator. So first the requirement of a pulse generator. If you have a square waveform, then you are calling the square waveform as a pulse waveform, then it should satisfy some of the conditions like this. So the first one, the pulse waveform should have minimum distortions. So whichever the signal we are taking, for each and every signal we are keeping the distortions as very much minimum. The basic characteristics of the pulse signal are the first one, rise time, overshoot, ringing, sag, undershoot. These parameters we have to monitor. So for each and every pulse waveform, we have to identify what is meant by rise time, what is meant by overshoot, what is meant by ringing, what is meant by sag, what is meant by undershoot. These parameters we have to see clearly for defining a perfect pulse signal. The pulse should have maximum amplitude, should have sufficient maximum amplitude. So whichever the amplitude you are defining for a pulse signal, that you have to give from the signal generator as much as maximum, so that the user can control how much voltage he required. The range of frequency control of the pulse repetition rate should meet the need of the experiment. So how many number of times this pulse has to reproduce for the user, based on the user requirement, we have to produce that many number of times this pulse. That is nothing but as pulse repetition rate. How many number of times the user required, that many number of times the machine has to repeat the same pulse. That is called pulse repetitive rate. Pulse generator can also be used as to produce triggering signals. Sometimes these pulse signals we are using for the triggering operations. For that reason, the pulse generator has to provide the output with a triggering circuit, with the triggering signals. The output impedance of the pulse generator is another important consideration. So this is very, very important. The output impedance should meet the user requirements. So generally, most of the instruments they will provide with 50 ohms output impedance or either 600 ohms output impedance output pulse waveform. So in our block diagram also we will discuss with three outputs. One is triggering pulse signals, second one is 50 ohms pulse signal, and third one is 600 ohms pulse output signal. These are three outputs we will get from our block diagram, that we will see in the next slide. Next, DC coupling is also very, very important for the pulse signals. Let us see the block diagram of a pulse wave generator. So for the square wave generator, there is no necessity of seeing a separate block diagram. If the duty cycle is 50%, automatically it is, we can use this type of signals we can use for the square wave signals. So here we have to bother about the pulse wave signals. Coming to this pulse wave generator. This is a pulse wave generator. So it may be pulse wave generator, it may be any type of signal generator. Any type of signal generator should have two types of blocks. The first one oscillator, second one is attenuator. So coming to here, this is the first one, signal oscillator. So that here first see the oscillator. The oscillator we are taking with the help of frequency control and with upper constant current source and with lower constant current source. With the help of these three blocks, we can show that we have some oscillator circuit. That means the oscillator attenuator both are available in this concept, and externally also we are providing some attenuators at the output stage. This is the output stage attenuators. But these three blocks are more than enough. It is consisting of attenuators and frequencies. So with the upper constant current source and lower constant current source, we are providing the magnitude, that is amplitude of the signal, and frequency also we are defining here only. Right. So this block diagram almost similar to the function generator block diagram. In the function generator we have seen the frequency network control operation, and this frequency control network is connected to the upper constant current source and lower constant current source. In the function generator block diagram, the upper constant current source and lower constant current source, these both are connecting to an integrator. The integrator output is the integrator output is the triangular wave output signal. The output of the integrator is a triangular wave signal. But our concept is a square wave and pulse wave generators. Particularly this block diagram is pulse wave generator. So for that reason we don't need the triangular waveform outputs. So we have to remove that integrator part which is representing with these dotted lines. Now we have to bother about the square wave output. So for that reason, this upper constant current source and lower constant current source, these two current sources we are connecting to a switching network. We are connecting to a switching network, a switching circuit. This switching circuit is connected to the schematic trigger circuit. So the output of the schematic trigger circuit is nothing but as a pulse signal. The output of this schematic trigger is pulse signal. Right? At this place, we will get the pulse signal. Right? At this place, we will get the pulse signal based on our required pulse width. Okay, so that is the pulse waveform we will get at the output of this schematic trigger circuit. Right. So this schematic trigger circuit is synchronized with the synchronization input with x-axis and y-axis informations. For synchronization purpose, we are providing an external and internal synchronous circuit. This synchronous circuit is also connected to the schematic trigger circuit. So finally, the schematic trigger circuit which will produce the pulse waveform. This pulse waveform we are directly taking, and the direct output we are taking here with the 600 ohms output impedance. The schematic trigger output after the output amplifier, it will give 600 ohms output impedance. Right. So the default output impedance is 600 ohms. If you require a specific output impedance, then you have to use that related amplifier. For example, in this picture, we have taken 50 ohms output impedance pulse waveform. So for that reason, here we have taken 50 ohms output amplifier. 50 ohms output amplifier here we have taken. With this output amplifier, we will finally get the pulse waveform with 50 ohms output impedance. And the same pulse signal we are giving to the triggering output circuit. We are giving the triggering output circuit. At the triggering output circuit, we have the positive and negative polarity. Based on the polarity, we are selecting here by using triggering polarity knob. We can get the triggering output circuits. We will get the triggering output circuits. So this is the total block diagram explanation. Now let us see the upper and constant current source, how they will produce a square wave based on our requirement time periods. That we will see in the next slide. In this slide we will see the theoretical information for this block diagram. So coming to here, the basic circuit for pulse generation is a asymmetrical multivibrator. This is nothing but as an asymmetrical multivibrator circuit. The frequency range of this instrument is covered from 1 Hz to nearly 10 megahertz, and with a linearly calibrated dial for the continuous adjustment on all ranges. In all the ranges of this pulse wave signal, we can adjust the complete frequency. The two independent outputs are available with a 50 ohms and 600 ohms, and here we have a 50 ohms supply of pulses with a fall time of 5 nanoseconds, 5 volts peak amplitude, and 600 ohms source. See here, 50 ohms, here we have two types of outputs. One is 50 ohms output source, and the second one is 600 ohms output source, and it has some fall time with 50 nanoseconds and output is 5 volts, and it has 600 ohms output, it has 70 nanoseconds rise or fall time and 30 volts peak amplitude. So two types of output impedances, 50 ohms output, 600 ohms output. For 50 ohms output, we have 5 nanoseconds fall time. For 600 ohms, 70 nanoseconds. 50 ohms output impedance has 5 volts maximum peak. Here we have 30 volts maximum peak amplitude. The instrument can be operated as a free running generator, and it can be synchronized with the external signal. So once if you switch on this equipment, it will work without any separate condition. That means it is a free running oscillator. It acts as a free running oscillator. Otherwise, you can connect any external source and you can sync this output with other external sources also. Right. So coming to here, how the pulse width we can vary. for the positive peak and negative peak. We can see the basic self-generating loop with the help of this small portion of the previous block diagram. So whichever the block diagram we have seen in the previous slide, the same block diagram, we are taking some portion, that is the upper constant current source here we have taken, upper constant current source here we have taken, and lower constant current source here we have taken. Upper constant current source we are representing with I1, and lower constant current source we are taking I2. This is which either connects to I1 or I2. I1, which is nothing but as the current we are getting from the upper constant current source. With this current, the 𝑠𝒖𝒕𝒚 trigger is operating, and the 𝒖𝒕𝒚 trigger will give the high level logic output. When the I2 current is switched to the 𝒖𝒕𝒚 trigger circuit, then the lower current, that is low level logic, we will get at the output of the 𝒖𝒕𝒚 trigger circuit. That is based on our operating time. How much time we are connected with the I1, that is defines with this T1 time period. How much time we have connected this I2, that is that will decide the time period of T2. So here the pulse width T1 and the remaining pulse period we are defining T2 with the help of this upper and lower constant current source, that is I1 and I2, right? So generally, if you are using an integrator, then for when the upper constant current source is we have, then the output voltage is linearly increasing. When the lower constant current source is there, then the lower constant current source, if it is driving at the 𝒖𝒕𝒚 trigger, we will get the output voltage as continuously linearly decrementing output voltage. So this is also called basic generating loop, basic generating loop, T1, T2, T1, T2, T1, T2, like that we will get a continuous signal from this basic generating loop. So coming to that, this basic generating loop, the upper constant current source supply a constant current to the capacitor, and the capacitor voltages increases linearly. So when the constant current source we have connected to the 𝒖𝒕𝒚 trigger circuit, the same current is driving this capacitor, and the capacitor is charging linearly. That is, we will get this waveform. This is the continuous charging, the continuous increment, linear increment curve we will get. When the positive slope of the ramp voltage reaches an upper limit, when this positive voltage maximum peak value if you get, then the upper limit is set by internal circuit components of the 𝒖𝒕𝒚 trigger circuit changes its state. So when this signal has to be raised down, that is decided by the internal components of the 𝒖𝒕𝒚 trigger circuit. The trigger circuit output becomes negative and reverses the condition of the current switch. So whenever this ramp curve want to decrease, the 𝒖𝒕𝒚 trigger will give a small signal. So with that small signal, the output is going to be decreased for a given set of time. Next. So coming to that, the capacitor discharges linearly when you are giving the lower current, I2 current, when you are connected to the 𝒖𝒕𝒚 trigger, the capacitor is going to be discharged. The discharged part we are representing in this fashion at T2 time period. When the negative ramp reaches a predetermined lower level, the 𝒖𝒕𝒚 trigger switches back its original state. So whenever the predefined level is reached at this rise down curve, at that particular time, automatically it switches to the upper constant current source. Then the upper constant current source delivers some current. With that current, the capacitor is going to be charged. At that time, we will get the linear increment curve, linear increment waveform as shown in this concept. How the linear increment will be observed. Next, the entire process is then repeated. So this process is continuously repeated. The ratio of I1 I2 determines the duty cycle. How much current you are giving at the I1 and I2, this ratio will decide the frequency or the time period or pulse width of the signal. The sum of I1 and I2 determines the frequency. The size of the capacitor is selected by the multiplier switch. The I1, by combining I1 and I2, we can say that this is the frequency. Like that, we can declare the frequency values with the help of I1 and I2 current timings. The unit is powered by an internal supply that provides regulated voltage for all the stages of instrument. Internally, we are placing a power supply circuit that is that is going to power up all the circuit components. Okay, so this is a basic self-generating loop in the pulse generator block diagram. Okay, so coming to here in the pulse generator block diagram, the most important one, the upper constant and lower constant current source, how these constant current sources are driving this schematic trigger is very important, and the selection of the components in the schematic trigger is very important to get the correct frequencies for I1 and I2. Okay, so these are the very important parameters we have to remember in the pulse wave generator. Okay, thank you.